Everybody likes electricity. We use it for lights, electronics, Halo 3, and a number of other things. Well, there's not really a whole lot of different places electricity can come from. The one that I'm going to talk about today is nuclear power and what makes it safe. Nuclear power has a lot of bad stigma surrounding it. A lot of people think that it's really dangerous, creates all kinds of radioactivity, it's going to make you have, three heads, deformed kids, crazy stuff like that. The reality is, that's not true. Nuclear power as an electrical power source is actually really safe. One of the reasons for that is that we rely on delayed neutrons to make the reactor critical. Critical just means that the power's not changing. It's good. Anyhow, nuclear fission is the splitting of uranium-235 atoms. You get an average of about 2 neutrons per fission. And most of them are born prompt, which means that they're born or are free to interact with other atoms before 10 to the minus 14th second from the event that caused it, or the fission. Delayed neutrons, on the other hand, is any neutron that occurs after 10 to the minus 14th second from the event that caused it. I have up here the neutron life cycle and some simple definitions. This will help explain a little bit better about how delayed neutrons make reactor power safer and controllable. Now right here you've got fast neutrons, newly born fast neutrons, and I'm not going to go into all of them. It's just a bunch of the factors that go through that explain where all the neutrons come from and how their numbers are diminished, not used. They leak out of the core, they get absorbed by other things that don't cause fission. Anyhow, right here we have beta, which is the delayed neutron fraction. It's 0.0065%. So that's the percent or the fraction of all neutrons that are born delayed. Down here we have beta bar, which is effective delayed neutron fraction, and that's 0.0075%. The reason that that one's just a little bit higher percentage is because delayed neutrons are generally born with a lower energy. Now, for the reactors that we use, we rely on thermal fission, which basically means neutrons at slow or thermal speeds to cause the fission. Well, the neutrons born at a lower energy level have to be, or don't have to be moderated or slowed down as much, so they're more likely to cause fission, meaning that the effective delayed neutron fraction is a little bit higher. Anyhow, the generation lifetime, or the time for the neutron to go all around this and start the whole thing over again, is significantly longer with the presence of delayed neutrons. Because we have that 0.0075% of delayed neutrons in there, they have an average of 1 to 100 seconds from the time from the event that caused them. So it greatly slows it down. Doesn't seem like a whole lot, but when you're talking that most of them are at 10 to the minus 14th second, when you average in between 1 and 100 seconds, it makes the number a lot larger. Actually makes it somewhere around 1/10 of a second for a change in the generation, and that drastically slows down the amount reactor power can change, because that's what makes it different from a nuclear bomb. Those are prompt critical, meaning that they become supercritical on prompt neutrons alone. So because of that, the generation lifetime not only is a lot faster, but speeds up exponentially. Vaporizing cities and stuff like that. We need controllable power, and the delayed neutrons help us do that by keeping the reactor power controllable and slowing down at the rate it can change, so the operators or safety systems can react and insert the control rods to absorb all these extra neutrons to shut down the reaction. Anyhow.
That was easy.